Good morning. Finishing up with finish up transformation. We're looking at the matrix of transformation. You can kind of think of this as a coordinate matrix for the transformation. And so then what's going to wind up happening is you use your coordinate vectors. So it's going to be the coordinate matrix times the coordinate vector. That will give you the coordinate vector at the output, which you can then convert back to your regular vectors. So you're going to need two ordered bases, one for your domain, one for your codomain. There will exist a unique matrix A, such that for every vector being V, the coordinate vector of L of V with respect to T is just A times the coordinate vector of V with respect to S. The J column of A is, that should be an L, not an F. I'm going to fix that. Right, it's just L of your J vector in the ordered basis for S, and that coordinate vector. That would be your J column. So you have to transform every element in the basis of S using L, find their coordinate vectors, and then form your matrix where each column is one of the coordinate vectors. Okay, no, okay, that's nice. No more references, so we'll see how this goes. So kind of a pain, depending on the ordered bases you use to find the matrix. However, analyzing the linear transformation using its matrix is definitely a lot easier. Because last time we looked at the kernel and the range, right? Well, if we have the matrix A, then the kernel is just the null space of A. And the range is just the column space of A. And those are generally a lot easier to find than the kernel and the range. Now that kind of just says what I just said. As long as V and W are finite dimensional vector spaces, ordered bases S and T respectively, L is a linear mapping from V to W, whose matrix is A. And then rank of L is rank of A, nullity of L is nullity of A. Should clarify, the null space isn't the same because you have the coordinate vectors, but then you just transform those into your original vectors, and that would give you the kernel. Same thing with the comp space in A, but they're related. So it's easier, it's still easier to find the null space and column space of your matrix and then convert them back. And so we're going to have a linear operator on R2. Remember, linear operator is just a linear mapping whose domain and codomain are the same. This operator is defined by g of xy equals 2x minus 7y, 4x plus 3y. We're also going to consider the ordered basis, 1, 3, 2, 5 for R2. We'll go ahead and find the matrix representation of G relative to that ordered basis, and then verify that A times the coordinate vector of V is just the coordinate vector of G of V for the given vector. I'll let you verify on your own that that actually does form the basis for R2. Here's what we have to do. First, we have to transform each of the basis elements. Back here. So take 1, 3, plug it into G. Do what? 2 times 1, 7 times 3, 21, 2 minus 21, negative 19. There's your first entry. 4 times 3, 12, oh, I'm sorry, 4 times 1, 4, 3 times 3 is 9, 4 and 9, 13. So negative 19, 13. Is that right? Yes. We now want to find the coordinate vector for that. Right, that is, we want the constants A1 and A2. such that that vector is a linear combination of the two basis vectors. Before I tackle that, let's just transform the second vector as well. So plug 2, 5 into the mapping. What are you going to get? You're going to get 2 times 2, 7 times 5, 4 minus 35, negative 31. Then it would be 4 times 2 and 3 times 5, 8, 15 is 23. What's that, negative 31, 23? We want its coordinate vector. We want the constants b1 and b2 that make this true. Well, how would you solve that first equation? Set up our augmented matrix, right? That's what we're having. We're reduce it. But wait a minute. Solving this one, coefficient matrix is the same, isn't it? You're just augmenting it with a different vector. Well, what do you think would happen if I just added another augment onto here? It would solve both of them simultaneously. So why set up 2 different matrices when you can just set up one matrix? So you cut your work in half. And you're really welcome to do that by hand if you want to. I won't stop you. I think I need to adjust this. A was what? 1, 2, negative 19, negative 31. Three. that what we got?
Yeah.
I'm saying more than welcome to do it by hand. There's where we're at. But this is our coordinate vector for 1, 3, or the transformation of 1, 3. This is our coordinate vector for the transformation of, what was it, 2, 5. Both of these columns make up your matrix. So that's the matrix representation of this mapping with respect to the given order basis. Now they just wants to verify that the coordinate vector of G of V is A times V. Or A times the coordinate vector for V. Let's just do G of V first. I don't know why I wrote it that way. What are we going to get? 2 times 4, 7 times negative 3. That's what, 8 plus 21? 29. And then 4 times 4 and 3 times negative 3. 16 minus 9, 7. That's what, 21, 7. Or sorry, 29, 7. We need that coordinate vector as well as the coordinate vector for V with respect to the basis. Again, that would give us the coordinate vector for V, right? If I instead augment it with 29, 7, it would give us the coordinate vector for G of V. Right? So why not just set up a single matrix to row reduce it and then interpret that? Oops. Is that what we got? There's our coordinate vector for V. There's our coordinate vector for G of V. Now we just have to do that. No, you can do 121 times negative 26 plus 201 times 15 in your head, right? Now you have 131, 80. Is that the coordinate vector for G of V? So it's verified. New operator, this comes on R3. Test, and I think for the sake of time, I won't verify. We'll just go ahead and find the matrix. Again, the first thing that we want to do is find the transformation of each of the three, in this case, basis vectors. G of 1, 1, 1, 3, negative 3, 3. At least these basis vectors are nice to work with. That's what G of 1, 1, 0. 2, negative 3, 3. Last one was 1, 0, 0, right? 0, 1, 3. So we take our coefficient matrix where each column is vector of the basis, augment with our first transformation. And remember, instead of setting up three separate matrices, just set up one. Now we're going to augment with 2, negative 3, 3. And then we're going to augment with 0, 1, 3.
Could we just reorder the vectors and the bases to automatically put it in? Like we just put like the third vector first and swap the first and the third vector? Would we just be done? Or is that not allowed?
You could, but still would be RR, yeah.
Yeah, but like that,
It would make it easier.
it makes it easier. So we could do that for on the test or whatever.
You could, but be careful with that because it's also going to change your coordinates around as well.
Yeah.
So I would not do it. I would treat it as an ordered basis, which means the order doesn't matter. So yeah, it's not really said in here, but it is implied that with all of these problems, they are ordered bases. And we'll reduce that. Everyone get that? As the variables? Of course, I don't know why I'm still showing it after that project we're all mastered with mathematics anyway. Oh, by the way, ChatGPT did a terrible job with the solutions. I had to pass it through like 10 times to actually get it correct. It did eventually get it, but I had to keep telling it, hey, you may want to recheck this. You may want to recheck this. Yeah, you may want to check this again.
Hey, does ChatGPT because of errors?
What do you mean?
I mean, like, if you input the data, it just, it won't give you the answer because it can't really read what the question was.
I didn't encounter that one, no.
Whenever ChatGPT finds something that it doesn't understand, it will usually fill in some sort of made-up solution. It's just a fail-safe for it. You have to literally specify, do not make anything up, and that's when you'll get an error where it'll say, I don't know how to do this.
Yeah, it just gaslights you.
The biggest error I got was it didn't interpret the linear combination of vectors. It actually like tried to do it as like separate vectors. I don't know what the hell it was doing. And then it got the encoder completely wrong. And the decoder completely wrong. I don't know what it was doing.
I mean,
That's
it
okay.
encrypted it a lot better than what the regular solution was, because it's completely random.
Hmm?
If you put in a thing to try to encrypt with ChatGPT and it makes something up, doesn't that make it a better encryption?
Yes and no.
I mean, no one will be able to
It's
decrypt
better
it.
encrypted because you're not going to know how to decrypt it. The problem is the person you want to decrypt it won't be able to decrypt it either. So it kind of defeats the purpose of the message. Yeah, may encrypt message. I have your wife hostage come 2 p.m. or throwing her off the bridge with a rock tied to her. And it never decrypts right, so now you don't get the money and you're now a murderer.
That's what life insurance is for.
So our matrix representation, right, is those last 3 columns. That would be the matrix representation. Now again, with respect to that ordered basis, right, if you used a different ordered basis, you have a different matrix. Okay, cool. And so, a lot of what we've been looking at least in class, if you've actually been watching the videos, which I know you all have been, you should have seen some different types of operators. But in class, we've only been really working with polynomials and vectors. We did a little bit of matrices. Until now. So consider the vector space V of all functions from the reals into the reals. This This said e to the 3t, t e to the 3t, t squared e to the 3t forms a basis for our vector space. D is the differential operator. And so D is going to be from V into V. We're going to find the matrix representation of D with respect to S. What's the derivative of e to the 3t? Oh, you mean calc 1 bears that. What's the derivative of t e to the 3t?
Would it be 3t squared and 3t?
3t each of 3t.
Well, it's not by parts, that's integration. We're not there.
Three T e to the 3t.
3t to 3t plus e to 3t.
Yes. What rule is that?
I don't know what it's called. Is that a chain rule?
Chain rules where the 3 comes from.
Okay.
Chain rules for composition of functions. It's very obvious what it's called.
Multiplication.
What's another word for multiplication? What's the result when you multiply two things? It's called- It's the product rule. It's the product of two functions. So it's the product rule. But I'm not going to write it the way that you gave it to me. I'm just going to switch the order. No, it should be, sorry, just e to the 3t. Plus 3t e to the 3t. What is the derivative of t squared e to the 3t? Yeah, by parts is when you deal with the antiderivative operator. Which, by the way, that's also a linear mapping. If you only consider the simple antiderivative. So I could also do that and make you do integration by parts on those.
We said 2t e to the 3t plus t squared 3e to the 3t.
Measure derivatives. Oh, no one said we'd have to do calculus in linear algebra. But honestly, what would you rather do, have a Calc 1 exam or another linear exam on vector spaces? So that's my case, right? This is a little reprieve. Yeah, just wait till you get the differential equations. Then you say, I wish I could go back to linear.
I did it already. Now you.
Isn't it amazing that they let you do differential before linear? Because you actually need linear for differential.
Yeah, he was.
I hate that community colleges do not have linear algebra as a hard requirement. for differential equation. They don't even have it as a code right. It's stupid. Then I get to that part of linear differential equation, I go, and I need linear algebra for this, so you just have to take my word for it, because you have no idea what the hell that name this means. You'll learn when you take linear. But remember, we want to write each of these as linear combinations of the basis vectors. If you already have differential, that means you're really looking forward to eigenvalues. Remember doing those when you're solving systems of first order linear? Okay. Now we're going to tie it all together, because I'm going to tell you what an eigenvalue really is. Maybe it's one of the examples I'll do a system of first order differential equations and application, which I bring back to linears. Did you do power series solutions? Yeah.
We work with power series a little bit.
You wouldn't forget if you did power series solutions, because those are the worst part. Those are the worst part of the OED.
That was what, 2 years ago?
You shouldn't need to set up a system for this. Should be really obvious what each coordinate vector is, right? What's alpha 1? What's alpha 2? I agree, alpha 1's 3. What's alpha 2? Do coefficient comparison. Do you see a t e to the 3t?
Is it 3-2?
It's 0. Derivative of e to the 3t was 3e to the 3t, right? Is there a t e to the 3t in that derivative? No, so alpha 2 has to be 0. What's alpha 3? It's also 0. There's no t squared e to the 3t. Your first coordinate vector is 3, 0, 0. What's beta 1? What's beta 2? What's beta 3? So your second coordinate vector, 1, 3, 0. What's gamma 1? What's gamma 2? Two. What's gamma 3? The third coordinate vector is 0, 2, 3 in their dimensions. This one required no work. It was just coefficient comparison. But again, that's only with respect to that basis. If I gave you a different ordered basis, your matrix would be different.
Should I do 2 and row 3?
Zero, zero, two, you're saying?
Or, no, 0, 0, 0, 2, 2.
So what should be the row 3?
Shouldn't the second 0 in on column 2 for row 3 be a 2?
Second column, row 3, you said?
Yeah. Second column,
It should be a 2.
why? Because wasn't it gamma TE to 3T?
Column 2 is the betas though.
Oh, okay.
Remember, each column is a coordinate vector. Right, so column 1 is the coordinate vector for your first, which is all your alphas. Column 2 would be all your betas, and column 3 would be all your gammas. Here's the question. Do I want to prove that? Maybe if I have time, I'm missing a question on here. Why am I missing a question? I'll find it. If I have time, I'll come back to it. Otherwise, I'll make you prove it on your own. So F is a linear mapping from R3 into R2. Now we're not dealing with operators, we're dealing with an actual mapping. Which means we're going to have 2 sets of ordered bases. S and S prime, let's call them. We're going to find the matrix representation of F with respect to those 2 ordered bases, S and S prime. We want to start off still the same way. I'm going to transform each of your basis vectors from the basis of the domain. So we're going to start with transforming all of your vectors in S. What does 1, 1, 1 map to? What was it? Didn't sound too confident. One negative one, I agree. You next want to transform 1, 0, 0. What does 1, 0, 0 map to? I'm sorry, not 1, 0, 0. I wrote 1, 1, 0. What does 1, 1, 0 map to?
-4.
Final one, 1, 0, 0. What will 1, 0, 0 map to? What we now need to do is find the coordinate vector for each of those transformations with respect to the basis of the codomain. In this case, S prime. Well, the coefficient matrix would just be 1, 3, 2, 5, right? By columns. And then we're going to have 3 augments, right? One for each of the transformations. I mean, to reproduce that. Is that what we got? A matrix is the matrix formed by taking each vector in that row reduced augmented and making that a column. There's our matrix representation. Let's see if we can find that missing problem. No, I just never did it. No, I feel like it's writing it out here. Oh, well. Now, obviously, the easiest matrix to find would be the matrix relative to your ordered standard bases. That'd be the easiest one to find. But when have we ever done anything that was easy? I guess technically we just did, right? There, that was easy. The derivatives. Do we have any questions on the matrix of a transformation? Again, it's more row reducing. First, let's this. The homework on this stuff due the 22nd. The April 22nd, which is next Tuesday, right?
No, I'm just saying, it's a 26th meeting. This meeting is on the 22nd.
What'd you say?
It's our 22nd meeting, and that's due on the 22nd. I just wanted to-
Oh.
I thought it was next week.
Now I'm going to stop recording so this part doesn't show up. I'm generally too lazy to do a lot of editing.